RF Man here. Today I want to talk about RF splitters and combiners. I recently watched some videos on YouTube that talked about this topic, but they really didn't go into detail on how the splitters and combiners are designed and how they operate. So I wanted to take a few minutes today and talk about that and show some of the details. So here's a typical combiner and splitter, and incidentally, any combiner can be used as a splitter and any splitter can be used as a combiner. This is the splitter, which generally has a lower power rating. This is the combiner, which generally has a higher power rating. Here's the diagram of a typical splitter combiner. So as a combiner, P1 would be basically used with P2 and P3 and vice versa. So to split the signal, we put the input signal on P1 and we split it out on P2 and P3. So this is my input, this is my outputs, okay? As a combiner, we combine the two signals, okay, P2 and P3 as the input and P1 as the output. So this is the version that I built. I'm building this for a project right now, and I just stacked my ferrite cores just to save room on the PC board, and I'm going to be demonstrating this with the Nano VNA to show some of the characteristics. So you can see this is a two-way, say one input, two outputs, or two inputs, one output, depending on if I'm using it as a splitter or a combiner. So that's my version. So let's talk a little bit about what this is. We already said that RF splitters and combiners are basically multi-port devices that can be used to split or combine an RF signal. So any splitter can be used as a combiner and any combiner can be used as a splitter in most cases. And the performance characteristics for this technology, we want to have a low insertion loss. We're going to be demonstrating that on the Nano VNA, so we'll talk about what insertion loss is. We want to have a high amount of isolation between the ports, so we'll be able to measure that as well. A characteristic impedance of 50 ohms. Low SWRs, 1.2 or lower. 1-to-1 is ideal, so we'll try to get as close to that as we can. And then we want to have a low phase shift and amplitude imbalance. Okay, so when we're using this, we don't want to have the signals shifted in phase, and we want to have the amplitudes as close to being balanced as possible. And we want to have the proper power handling capabilities. So what determines the power rating? You could see in this size here, I'm using relatively small ferrite cores and RG316 coax. So power rating on this is limited to about 50 to 100 watts. If we want to have a higher power rating, then we would basically use a larger core with heavier coax. And that's what you saw in the diagram a few minutes ago. Okay, so let's move on. So basically, we're going to be talking about the type of combiners and splitters that are designed with transformers. There's many other types that I'll be showing, but we're going to be focusing on the type that uses auto transformers. So what's an auto transformer? We're going to take a look at that for those of you who are not familiar with that technology and talk about how that works. So basically, we have a common splitter combiner that consists of two auto transformers. One basically transforms the impedance from 50 ohms to 25 ohms, and the other transforms the impedance from 25 ohms back to 50. So we talked about the core and the size of the core. Just wanted to add another note here that if our core size is not large enough, what we would typically see is the core may be saturated, particularly at lower frequencies, and this can cause signal distortion and reduction in isolation and harmonics. So the general guideline is that the impedance of the transformer should be at least 5 times the characteristic impedance, which is 50 ohms. So we're going to talk about exactly what that means. I'm using material 43, which has a higher permeability than some of the other materials, and this gives me the high impedance. So we'll show you how to measure that and how to calculate what that impedance is. Okay, so I already mentioned that there are different types of splitters and combiners. So here, this is a resistive type, okay, uses 2 resistors on, we'll say, the input side and 1 resistor on the output side. The concern with this is there's a lot of loss because we're using resistors, so it is lossy. Then there's a Wilkinson combiner, which uses quarter wave transmission line. Okay, there's a lot of examples of this on the internet. And the third type, which is the type we'll be focusing on today, is called the hybrid splitter and combiner. And as I already mentioned, it uses 2 auto transformers. So now with this type of technology, it could be a 2-port, 2-way device, or it can be what's called an N-way device. So you can have 1 port, say, as the input, if you're using it as a splitter, and then multiple ports on the output. All right, if we're using it as a combiner, then vice versa, multiple ports on the input, 1 port on the output. So they call that typically an N-way splitter combiner. Okay, so let's talk a little bit about what an auto transformer is, and I think the best way to understand that is to compare it to a conventional transformer. So I think most of us are familiar with conventional transformers. We have basically a primary winding and a secondary winding, and then we have a turns ratio of the primary, a turns ratio of the secondary, and that basically determines what our output voltages would be. So we have an input voltage V1, output voltage V2. Okay, with this type of transformer, it uses mutual electromagnetic induction, and this provides galvanic isolation between the windings, electrical isolation. So the primary side is completely isolated from the secondary side. So we typically use these type of transformers in power supplies, on the mains, for example, and we have complete isolation between the primary side and the secondary side. So let's see how this works. It's very simple, just using the turns ratio. So we have V2 equals V1 times the ratio between the secondary and primary windings. So if V1 equals 100 volts, and the primary is 50 windings, the secondary is 25 windings, then 100 times 25 divided by 50 is 0.5. We have 50 volts on the output. Very simple. It's just turns ratio determines the output voltage. Okay, now let's take a look at an auto transformer. Okay, you can see there's only a single winding. Okay, so we have no isolation between the primary and the secondary. Okay, these are coupled using self-induction. Okay, so again, there's no isolation. So if we look at how to calculate the output voltage, it's basically the same. Okay, we have the primary windings, which are all of the windings in the transformer on the primary side. And then we have our secondary windings, which is where we put the center tap. Okay, so in this case, the center tap is right in the middle, but it doesn't necessarily have to be that way depending on the turns ratio that we're looking for. But the calculation is the same. V2 would be equal to V1 times the secondary divided by the primary windings. So if we had 100 volts on the primary, and then our primary winding is 50, our secondary winding is 25, so that means this would be 50 turns, and where the center tap is, only 25 turns. And then we have the same calculation, 100 times 25 divided by 50, which is 0.5, gives us 50 volts. So basically, to determine the output voltage and current, you use the same calculation, and it's the same relationship that you see here. Okay, and we all know that with a transformer, whether it's a conventional transformer or an auto, incidentally, the word auto means self in Greek, okay, whether it's an auto transformer, that it's basically the turns ratio that determines the output voltage. So if we step down the voltage, which is the case here, we step up the current, okay? And if we step the voltage up, then we step down the current, okay? So the relationships are opposed to each other. So that's what an auto transformer is. The takeaway here is I'm using the total number of windings and then the windings where the center tap is. That's an important point there. So let's take a look at the splitter combiner, the hybrid type that we're talking about. Here is my two auto transformers, okay? And what are we doing here? Okay, it's a little complicated looking at the diagram, and this can be drawn many different ways, so I'm going to show a number of different examples, but it looks a little complicated, but it's actually very simple. Okay, and what we're doing is we've got two ports here. Let's say we're using this as a combiner. Okay, we have two ports here, and the characteristic impedance of each port is 50 ohms, right? So we got 50 ohm systems here. But because these two ports are in series with the first transformer, okay, there's actually 100 ohms here, okay? And the center tap is, we've got 2 turns of the shielding and then 2 turns of the center wire, and it's center tapped in the middle, okay? So basically, if you look at the turns ratio, okay, for T2, the turns ratio is 2, right? And we know the turns ratio squared is equal to the impedance ratio. So the impedance ratio is square root of 2 is 4. Okay, so what are we doing? We're transforming the 100 ohms, which is in series with this transformer, to 25 ohms. Okay, so it's center tap, so we have two windings. Turns ratio is 2, impedance ratio is 4. It's a 4-to-1, so the impedance transformation is our 100 ohms to 25 ohms. So let's look at the other end, okay? This then takes our 25 ohms and transforms it back to 50 ohms. So here we have a total of 4 turns, but it's tapped after 1 turn, okay? So if we go through the calculations, it's basically 4 turns to 3 turns, okay? 4 turns is the total. 3 turns is where we have the tap, okay? So the turns ratio is 1.33. If we square that, it's 1.8. So we say impedance ratio close to 2-to-1. So it transforms the 25 ohms back to 50 ohms. Okay, so that's what the schematic looks like. So let's take a look. Here's a diagram, and I put this up on my notebook so it might be easier to see. But on the 2-to-1 side, okay, which is here, we said we had 1 turn and then 3 turns, and we said they're in series. Well, that's not immediately apparent when you take a look at this, but if you break it down, you'll be able to see that here's the shielding, okay? And here's our 1 turn, all right? And then what do you see? You see a jumper wire. This is the center tap on the schematic, right? Then we have our 2nd turn, okay? And that's connected to the center conductor, okay? And then we have 2 turns of the center conductor, which goes to ground. So these 2 windings are just in series. It's that simple, and that's what makes it an auto transformer. That this point here joins the shielded winding with the center conductor, and you have 2 turns and 2 turns with the center tap after the single winding. So let's take a look. It's exactly what we have here, right? We have 2 turns and 2 turns, so 4 turns, 2 for the shield, 2 for the center conductor, but it's center tapped after 1 turn, okay? So that's what gives it this ratio here, okay, where we have 4 turns to 3 turns, okay? And then turns ratio squared is equal to impedance ratio, which is, as I'm showing here, 2 to 1, okay? So that's how this side of it works, okay, to convert the 25 ohms to 50 ohms. And it's very similar if we take a look now at T2, okay, which is the 4 to 1. Okay, we see here's our center tap, okay, here's our shielding, and here's our center conductor. So I have 2 turns of the shielding, 2 turns of the center conductor, total of 4 turns, but you see the jumper is right in the middle, so that it is center tapped. And then the outputs are across the isolation resistor. One output is the center conductor, the other output is the shielding. So you have to look at this close to understand, but they're just in series. These are just auto transformers. That's all they are. So let's go back to the schematic, and you can see I got 2 turns of the shielding, 2 turns of the center conductor. You can see where they're tied together. You can see the jumper is center tapped to the transformer. Okay, and then we have our isolation resistor, which is 2 times the characteristic impedance. So we said 50 ohms, right? So it's just 100 ohms, right? And that's what this transformer sees, because the characteristic impedance is in series. So what does this do? Basically, it takes the 2 inputs, okay, which are equal to 100 ohms at the transformer's inputs, okay, and it transforms them to 25 ohms, and then the 2 to 1 transforms the 25 ohms back to 50 ohms. And the isolation here is provided by this resistor. All right, and we don't want to have any kind of imbalance. If we're using this as a combiner, for example, we don't want to have an imbalance here, because the difference in the 2 inputs is going to create some power dissipation across the resistor. And that's why typically you see a pretty large resistor that's used, because it's hard to determine what system that's going in and how well it's balanced. So that's basically what the technology is, just 2 auto transformers. And we said we need to have a minimum impedance, right? So when we complete our windings and we measure the impedance, we're just basically going to measure the inductance of T1 and T2, okay, across my windings, and then we calculate the inductive reactance, right, which is inductive reactance equals 2 times pi times frequency times inductance in henries. So when we go through that calculation, we see at the lower frequency, it's 300 ohms. This would be worst case, right, because it's times the frequency times F, right? So if we increase the frequency, we're going to increase the impedance or the inductive reactance. So we use the worst case frequency, right? And it's going to obviously be higher than that as we go up the bands, right? From 160 meters to 80 meters to 40 meters, etc. So this would be the minimum. So it meets the requirements of at least 5 times. Actually, that's 6 times. So that gives us a high enough impedance. And again, we have to ensure that we maintain that impedance and that we're using the proper coax and proper size ferrite cores. So let me just reposition the camera here for a moment. Bear with me. That looks pretty good. Okay, so let's move on. This is another way to draw this, and the reason why I've included all these different schematics is because it's not always so intuitive when you look at them and realize, well, what is this, right? These are nothing more than auto transformers. So again, we have our 2-to-1 and our 4-to-1, and we have, if you look at this particular schematic, and this one is pretty common out there if you did any kind of Google searches. But you see we have one turn of the shield here, and then we have another turn of the shield here, and it's center tapped, right? And then 2 turns of the center wire, okay? So you can see they're in series, okay? If we go back on the 4-to-1 side, right? Here we have our 2 inputs, and we have our isolation resistor. And as we saw in the diagram, right, we have 2 turns of the shield and then 2 turns of the center conductor, okay, and it's center tapped right in between. Okay, so this is just another way of drawing the same thing. So I thought I would show that. There's many ways to draw that, and here are the actual calculations down here that you can look at. Okay, and to make things even more complicated, here are some other versions that I found. Just doing a quick Google search. But again, when you look at these different schematics and you understand that these are just auto transformers and that the windings are just in series, it gets a little clearer, okay, when you start taking a look at these things. And incidentally, they don't always use the exact number of turns. Okay, they're just showing it as an inductor. But in my example, I wanted to show 1 turn and 3 turns, and I wanted to show 2 turns and 2 turns and center tapped. So it's very clear, okay, but that's not always the case with some of these diagrams. So just keep that in mind. But the approach is the same. You've got the windings in series to provide the 4-to-1 and 2-to-1 impedance transformation ratios. You'll also see that there's some capacitors used here. My version does not have a capacitor because I used all coax, but typically, let me go back to this photo for a minute. Okay, you see there's 2 capacitors here. All that's doing is giving this trace the characteristic impedance of a length of coax. Okay, so we have to add those. But I'm using all coax, so didn't really see the need for that. And when I did my measurements, it seemed fine. Okay, so the next portion of the video, we're going to be taking some measurements on the Nano VNA, and we're going to be looking at, as I already mentioned, insertion loss, and then the amount of isolation, and finally the SWRs. So we'll be doing some demonstrations on this in the second part of the video. All right, so now I'm back. Before we begin, I just want to clarify one point. Earlier in the video, I kept saying center tapped, and actually the 4-to-1 transformer, which had 2 turns and 2 turns, is technically center tapped. And for the 2-to-1 transformer, we had 4 turns and 3 turns, so we just refer to that as a tap. Actually, auto transformers could have multiple taps, as some of you might already know. So now we're going to take a look at the insertion loss. So what we have here, we've got the Nano VNA set up. We're basically taking port 1, which is here. We're sending the signal out through the splitter combiner into port 2. And what this allows us to do is to measure the insertion loss of the splitter combiner. So what would we expect? We're taking a signal and we're splitting it. So for example, if we had 1 watt on the input and we split it, we're going to have 500 milliwatts on each port. So each one would be half the power, and the half power point in decibels is minus 3 dB. So what we're seeing here is minus 3.2 dB. So that's pretty good performance. I'm satisfied with that. And to check your instrument, it's always a good idea to see if we're getting an accurate measurement on insertion loss. Just bear with me here as I set this up with an attenuator. So here I have an attenuator that has minus 0 dB all the way to minus 30 dB. So we can use this to see how accurate our measurements are. So we'll use the minus 10 dB and we'll connect that to the Nano VNA. And we should measure around 10 dB. Okay, so you can see this arrow is my reference point, so this is 0 dB. And you can see with the 10 dB attenuator, we'd expect to have about 10 dB of insertion loss, and we're measuring minus 9.87. So everything seems to be working correctly. Next, we're going to go ahead and measure the isolation between the two ports of the splitter combiner, and then we'll measure the SWRs. All right. So now we're taking a look at the isolation between ports 2 and 3. So what we do is we take the output signal from port 1, we connect it to port 2 on the splitter combiner, and then we take port 3, we connect that to port 2 and see how much of that signal we're receiving. So a good design should be at least minus 20 dB, which is 100 times lower. Or better. And what I'm measuring in the middle of the band here is around minus 25 dB. So that's pretty good performance. And what that tells us is how much isolation we have between ports 2 and port 3. And much of that isolation is provided by the 100 ohm resistor that you see here. So that's how we measure isolation between ports. Next, we'll go ahead and look at the SW. All right, so now we're measuring SWRs. And basically, I'm using port 1. I'm going into one of the inputs of the combiner. And we're looking at measuring what is the SWRs terminated with a 50 ohm load. And I've got the other input terminated as well, and I'm measuring 1.02, but there is a very high amount of isolation between ports 2 and ports 3. So yeah, if I remove the 50 ohm termination here, I don't think it will affect the reading much. No, I'm still getting 1.02 SWRs, which is excellent. Anything 1.2 or less is good performance. So what this tells us is we've got a very good match through the splitter combiner to the 50 ohm load on the output. And when I made the other measurements, I had some of the inputs terminated and some with 50 ohms and some of the inputs open. So I would follow that. If you're doing your own testing, you should be able to get similar results. And I can measure the other port as well. And what would I expect to see? I'd expect to see the same result. So let's try that real time here. Okay, I can leave port 2 unterminated and look at port 3. And yes, I'm measuring exactly the same, 1.02. As you see there, that's what I would expect. If I reverse this and try it the other way, which I've already done offline, I get the same measurements. So that's the SWRs. And I am using, as I mentioned earlier, all 50 ohm coax to terminate to the connectors, and the leads are very short, so didn't need to use any capacitors for compensation. All right, so now one final test. Here I have a small 3-watt amplifier, and I'm driving it with a function generator, as you can see there. Basically running it around 20 megahertz and driving it to 3 watts. And we can see the output on the watt meter. So what we'd expect if we connected the splitter combiner and we use this as a splitter, we'd expect the power to be divided evenly. So let's go ahead now and put the splitter in line here. And you can do the same thing and just demonstrate it as a combiner. You'll get the same results. I don't have two small RF amplifiers, or I would actually add that to the demonstration. But this, I think, will suffice. Okay, so now we have the amplifier and we have the, in this case, splitter. And we measured 3 watts output. Now we should see about 1.5 watts. So let's go ahead and turn the amplifier back on. And yeah, I'm seeing about 1.5 watts or so. So we can see that it splits the signal. So that's the demonstration. I hope you found this informative. If you have any questions or comments, yeah, you can leave them under the video. Thank you very much. RF Man.